In the race to build bigger and smarter AI, there's this hidden speed limit. And if you try to push past it, things don't just get better, they can completely break. We're going to talk about a really fundamental challenge in AI architecture today, that razor-thin edge between raw power and total instability.
So, that leads us to the big question, right? How do you actually unlock that next level of AI performance without the whole system just collapsing on itself? This is the puzzle we are going to unpack, and trust me, it leads to a solution that is surprisingly elegant.
All right, so our story really begins with what seemed like a fantastic idea. It was this little architectural tweak that was designed to make AI models way deeper and more capable. But hiding inside this cool innovation was a really critical flaw.
Okay, to get what went wrong, we first need to talk about the backbone of pretty much all modern AI, the residual connection. The best way to think about it is like a dedicated express lane on an information highway. It lets the main signal just bypass all the heavy processing in a layer, which makes sure that information doesn't get lost or garbled as it goes deeper and deeper into the network. I mean, this simple idea is what made today's massive models even possible.
So the thinking went, if one express lane is good, what if we could build a multi-lane superhighway? And that was the whole idea behind something called hyper-connections, or HC. The goal was pretty simple: dramatically ramp up the network's information capacity.
And the concept, honestly, was brilliant. Instead of just one stream of information, HTC created a whole bunch of parallel streams. It even added these learnable controls. You can think of them like smart traffic managers that could mix and combine information between all these new lanes. This promised a huge boost in performance, all without the crazy cost of just making the whole model bigger. It really seemed like the perfect win-win.
But, and there's always a but, isn't there? This is where the problem showed up. By giving the model so much freedom, this completely unconstrained power to mix signals however it wanted, it introduced a catastrophic instability. This new superhighway had absolutely no speed limits and zero guardrails.
This quote from the paper really gets to the heart of it. Without any rules, the signals flying down this highway could either get amplified into something unrecognizable or just fade away into nothing. The system literally could not maintain a stable average signal. And layer after layer, this tiny error would just compound until the whole thing broke down.
So how bad are we talking? Well, at its worst, the signal could be amplified by a factor of 3,000. Can you imagine that? It's like a whisper becoming a sonic boom in a split second. That's what was happening inside the network, and it caused the entire training process to just collapse. The superhighway was crashing, big time.
So how do you fix a highway that's completely out of control? Well, you don't tear it down, you install guardrails. And in this case, those guardrails were built from a really beautiful, elegant piece of mathematics.
And that brings us to the hero of our story, Manifold-Constrained Hyper-Connections, or mHC for short. This is the fix. It keeps all the power and all the flexibility of that original idea, but it puts in a strict set of rules to keep everything stable.
And the difference is just stark. On one side, you've got the original HMC with its totally uncontrolled signal flow, which leads to this huge risk of signals either exploding or just disappearing. The result? Unstable training. But on the other side, you have the new mHSC. It brings in those mathematical guardrails, and that guarantees signal stability. And that is what lets you reliably train these massive, scaled-up models.
Okay, but how does it actually work? Well, the secret sauce is this special kind of mathematical object that perfectly, and I mean perfectly, balances the flow of information. And the process is actually pretty straightforward. First, you start with that original, powerful, but totally chaotic mapping from HC. Then you apply this really clever algorithm that basically forces that mapping to play by a new set of rules. And the result of that process is something called a doubly stochastic matrix. This is the key to the whole thing. So what in the world is that? It's just a grid of numbers with two really simple but really powerful properties. First, all the numbers inside it are either 0 or positive, no negatives. And second, if you add up any row, you get exactly 1. If you add up any column, you also get exactly 1. That's it. That perfect balance is the guardrail we've been looking for.
And this is exactly why it's so effective. This matrix acts like a perfect traffic manager, making sure that the total amount of signal flowing through the system stays the same. It forces the output to be a nice, neat weighted average, what's called a convex combination, of the inputs. No one signal can just take over and explode because its influence is capped by that sum to 1 rule. It keeps everything perfectly in check.
Now, this all sounds great on paper, but does it actually work in the real world? Well, the results, they pretty much speak for themselves.
I mean, you can literally see the proof. The connection matrix from the original unstable HSC is just a chaotic mess. Values are all over the place. But in contrast, the mHC matrix is orderly, it's balanced, it's totally controlled. This is the visual proof of stability in action.
And that visual stability has a direct impact on training. In these big experiments, the model with the old HC architecture just hits a wall. You can see this sudden sharp spike in the error rate where the training just completely broke. But the model with mHC, it trained perfectly smoothly, showing steady improvement the entire way.
So what does all that stable training actually get you? Better performance. mHC doesn't just fix the instability problem. It consistently beats the original version across all kinds of tough benchmarks, from complex reasoning to reading comprehension. It's not just more stable, it's actually smarter.
And here's the kicker. All of these massive gains in both stability and performance come at a really tiny cost. Thanks to some smart engineering, putting mHC into the mix only adds about a 6.7% overhead to the training time. It's an incredibly efficient fix. So let's zoom out for a second. Why is this one little tweak to the architecture so important? Because, really, it points to a much more fundamental idea for how we build the next generation of AI.
The really crucial point here is this. Just piling on complexity without any rules is dangerous. We're starting to hit the limits of that bigger is always better philosophy. These elegant mathematical ideas can give us the guardrails we need to build systems that are more robust, more efficient, and way more reliable. mHC gives us a blueprint for models that are both powerful and stable, and that's getting people excited again about smart network design, not just brute force scaling.
The researchers themselves summed it up perfectly with this quote. This isn't just some one-off trick. It's a new direction. It's a new way of thinking about how we design the huge foundation models of the future. And this leaves us with a really fascinating final thought. For years, the path to better AI has just been go bigger. More data, more parameters, more computers. But maybe the next great leap won't come from just sheer size, but from smarter, more elegant, and more stable designs like this one.